Okay, so we are back to our favorite non-linear complication, water vapor, and we had seen this nice relation between vapor pressure and temperature over pure water, because if you increase temperature and you want to increase humidity according to that exponential relation we had seen, then you need infinite source of moisture. If you just warm air on land, and if there's no moisture source, it doesn't necessarily continue to get humider, right? On desert, for example, it can get very warm, but the air remains dry, right? Anyway, so as temperatures get colder, humidity begins to disappear. As you get warmer, the humidity increases exponentially, right? So if you go back to our definition of specific humidity, it's the amount of humidity per unit mass of total mass of air. So rho, you can take unit volume and do it as just density. So density of water vapor divided by density of air, which is dry air plus water vapor. Okay, and can you guess whether moist air is heavier than dry air or lighter? Well, it turns out you may already know that moist air actually reduces the density of air. Okay, so obviously at some point, if you're on this curve, that is the saturation vapor pressure, right? So if you are here, you are undersaturated for that temperature, and you can cool it and bring it to saturation. Or if you're here, the vapor pressure is less, so you can reduce the pressure. So you, for example, like the air going up and expanding because of low pressure and cooling and condensing, right? So you can reach saturation by either cooling or reducing pressure, right? So saturation specific humidity is when air is completely saturated for the given temperature in this curve, and that is defined as using our ideal gas law again, rho water vapor, R water vapor times T, and we can define that using this relation, do rho V of water vapor divided by rho of air. So you have ES divided by RVT, that's our rho V, and P over RT. Remember, ES is saturation vapor pressure, P is pressure of the air, total pressure, which is partial pressure of dry air plus partial pressure of water vapor. Very simple. So this is just rho V divided by rho, so you get R over RV, R of the air divided by RV. Air, whenever I say air, it has water vapor in it, okay? Times EF over P, so partial pressure of water vapor divided by total pressure. Okay, so you can also define a relative humidity. What does that mean? As I said, for a given temperature, the air may not be completely saturated. So you divide the specific humidity, the humidity that is actually present in the air, which is below saturation, divided by saturation humidity corresponding to that temperature, times 100. So it's typically referred to in terms of percentage. So you say air is 85% humid, basically means relative humidity is 85%. So Q is greater than Q star, then condensation begins to happen, right? If humidity reaches saturation humidity and goes beyond, then condensation will begin to happen. That's the definition of saturation humidity. How do you do it? Obviously, we are heading towards lifting an air mass, evaporate near the surface, warm air, take up the moisture with it, go up, expand, cool down, and voila, Q can become greater than Q star, right? So you reach the condensation level ZC. So here is a clear example. You have the ambient temperature profile TZ, and then the surface temperature is warmer than the average profile. Okay, this is temperature, this is height. This is alternatively done as pressure and height, so you just have to get used to seeing what it is and then quickly get on with it. Okay, so air is got humidity, but it's rising. Since it's not condensed, it's just behaving like dry air. Remember, this is the environmental profile, so it's not dry or wet, it's the mix long-term mean, right? So dry adiabat is obviously steeper than the environmental lapse rate. We know that, as we saw in the dry adiabatic lapse rate. But it's not constant, because once you hit, if there is humidity in the air, as it expands and cools and reaches the condensation level where Q becomes greater than Q star, then the further ascent of the air is going to be affected by the release of that condensation heat. So now its lapse rate is different. Eventually it will reach the environmental value of T when it reaches, let's say, its neutral buoyancy. Okay, so rising, cooling, air condensing, humidity reaching greater than saturation, so you need condensation level. Further condensation is going to warm the air parcel, so you can see that it's not cooling as fast anymore, but eventually all the air is condensed and you're going to reach your neutral buoyancy, ZT. Okay, typically that could be the cloud top. Well, we'll see that later on. Okay, so that's a short podcast, but you should understand these relations properly, because humidity is a key variable, the most nonlinear variable, and its thermodynamics is going to be very interesting and very complicating in the real world. We are doing it just as an introduction and keeping everything simple, so be careful.